So our first step in any hypothesis step is our hypothesis. And say for example, we want to know if our studying, so our study hours, so the number of hours you study, if that is related to your grades. So I'm going to say that the more you study, the higher your grade is. So if the study hours increases, then your grade should also increase. So would say that there is a positive relationship here. And that's what I'm going to hypothesize for this test. But before we talk about that part, we need our null hypothesis. So this is the one we're trying to disprove. We're trying to prove this one wrong. So our null is going to be rho. And remember, rho is a Greek letter, and it is the population correlation coefficient. So R is the sample correlation, and rho, this P looking thing, the Greek letter, is the population correlation. We're going to have that equal to 0. So that means that there's no correlation. So we're trying to prove that wrong, that there's actually a correlation. And then our alternative hypothesis, or our research hypothesis, is going to be rho, which is our population correlation. We're going to have 0 here as well. But then, like some of our other tests, like back when we did a t-test, we could have less than, greater than, or not equal to. And we have the same thing here. So if we think there's a negative correlation, then we would do the less than, because a less than 0 is negative. If we think it's a positive correlation, then we're going to do greater than. And if it's a not equal sign, then that means it could be negative or positive. We're just not sure. We just are hypothesizing a correlation, but we're not saying in what direction. Now in this case, right, we are saying that there's a positive correlation between study hours and our grades. So we're going to put a greater than symbol here. And so our alternative hypothesis, or our research hypothesis, is rho, which is our population correlation, is greater than 0. And then the second part to our hypothesis test is always the assumptions, and we always have random sampling. That's not a surprise. So you want to have random sampling so that the p-value is exact, but a lot of times we don't have a random sample, or probably almost all the time we don't have a random sample, but you want at least to have an unbiased sample. And so for our example of grades as our outcome variable that we're looking at, we wouldn't want to just go to one college, like say Harvard, because that's just a different kind of person than if you took a random sample from all across the country. So you just kind of want to watch out to make sure, you just don't have one type of person, and you just want to kind of get a variety of people, and hopefully the same kind of people if you just took a random sample. So a lot of times we can't get a perfect random sample, because a perfect random sample would mean that you put everyone's name in a hat basically and randomly pick their names. But because not everyone wants to take the survey, they might refuse, or you might only have access to one college. Like say you're trying to do the survey at U of H. You have access to U of H because you go there, but you don't have access to the whole country. So if you just took a sample from U of H, it's going to be biased in some kind of way. Hopefully that wouldn't affect your results, and you might have to critically think about how that sample might affect your results. Anyway, that's something to consider later on if you're actually collecting your own data. And the second thing for correlation is multivariate normality, and we're used to just regular normality. You're like, well, what is multivariate normality? Well, before, we are only considering one scale variable at a time, right? We only had an outcome variable that was a scale variable, and our independent or predictor variable was nominal, was in categories. But now we have two scale variables, right? We have a predictor or independent variable that's scale. We have an outcome or dependent variable that is also scale. So now we have to consider the normality of both. Then you actually have to consider the normality of them together. And so this is kind of a 3D plot because we're looking at x and y, and we want both to kind of be normal together. And you don't have to understand this all the way, I just want to kind of go over it a little bit. So what that means is that for each value of x, so let's rewrite this. So for each value of x, y is normally distributed. So let's take study hours. So that would mean that if x is 1, we have a normal distribution. If x is 2 hours, we have a normal distribution for y. So these are y's. And then if x is 3, then we also have a normal distribution, and so on and so on and so on. And this is kind of hard to, think about in your head. So as long as you have an, that's big enough, around 30 or so, you should be okay about this assumption of multivariate normality. And sometimes we check this by looking at what's called residuals, but I won't go over that. So we just want to make sure we have a good sample size so this normality assumption is held up. Alright, and then the third step is usually, your alpha, and if I don't tell you differently, use 0.05. Alright? Because that's the most common one, and that's what we always use in psychology, so we're just going to make it 0.05. Then our fourth step would kind of be to collect data, but we usually don't write this down as one of the steps. And if you got the correlation and you do this by hand, you get R equals 0.88. I'm not going to go over the hand calculations, but if you go back to the bivariate phase, then you can figure out how to get this by hand. Another thing you need to know is the n, and the n is 4 in this case. So it's the number of people, okay? And that's important, right? We have 8 observations. Right? This would be 1, 2, 3, 4, 5, 6, 7, 8. So 8 observations. But we only have 4 people. 1, 2, 3, 4. So person 1 we'll make them purple. They had studied for 1 hour and they got a grade of 45. Person 2 in blue, they studied for 3 hours and got a grade of 70. Person 3, I'm put in green, they studied for 6 hours and got a grade of 97. And person 10 had in orange here, had a grade of 95 and studied for 10 hours. So there's 4 people. So N is the number of pairs of observations, the number of people. And each person takes this twice, and gives you two pieces of information, which is called an observation. Okay? So for a correlation, you can use a t-statistic. So, our correlation coefficient has a t-statistic. So it's symmetric. It looks something like this. An R can be, positive or negative. So that goes along with a t-statistic. A t-statistic can be positive or negative. And it's sort of like the t-statistics that we're used to. Now normally on the top here is the difference between the sample means. But again, we have 2 scale variables instead of just 1. And so we have a scale variable for the predictor variable and the outcome variable. But this is very similar. The R coefficient is the strength of the relationship, and that kind of goes parallel to having the difference between the means. It's like the strength of the relationship versus before we were having the difference between the sample means. Okay, so our test is about, is this correlation strong enough? Is there enough sample size, etc., to say that there's a significant correlation? So this is what is on top, the strength. Okay, so then this is going to be positive or negative. And then at the bottom here, I'm going to put this in blue. This is the standard error of the t-statistic for a correlation. And so here we have that, and you can kind of make parallels to the other t-statistics that we're used to. So here in yellow, this is kind of like the standard deviation, but for the relationship. So we're kind of taking into account that we have 2 scale variables. And so it's taking into account the relationship, the association. But it's sort of like the standard deviation that we're used to, just not exact. And so let me put this in quotes. It's not really a standard deviation, but it's the variability for the association, or for the relationship between the 2 variables. Not to get into too big of the details, but I just want to make kind of parallels, okay? And then at the bottom, this should be a little bit more simpler to understand. And here in green, we have the degrees of freedom. And so remember, we have 2 scale variables, so we have 2 standard deviations. So we have a standard deviation for our x variable, and we have a standard deviation for our y variable. And we subtract off how many standard deviations we have to calculate to get our degrees of freedom. So our degrees of freedom is the number of pairs minus 2, because we have to estimate 2 standard deviations, 1 for each variable. Before, in other tests, when we just subtract 1, we only have to calculate 1 standard deviation. So that's why we're subtracting 2 in this case. And you don't have to know too much about degrees of freedom for this class, but I kind of want to give you the foundation for it, because if you go on to other more advanced statistics, degrees of freedom get really important, because you don't want to underpower your test. So if you have a low degrees of freedom, you're going to have a low power. And the more complicated your model gets, the less degrees of freedom you have. Alright, now I'm going to go over the example and find the t-statistic for our example. So remember, r equals 0.88. Our n was 4. And I'm going to find the bottom, the standard error first. So I'm just going to call that SR for standard error of r. So SR equals the square root of 1 minus 0.88 squared over 4, because that's our n, minus 2. So we have the square root of 1 minus 0.77, because 0.88 squared is 0.77, divided by 2. And then 1 minus 0.77 is 0.23, so we have the square root of 0.23 divided by 2. And then we do 0.23 divided by 2, that's 0.115, so that equals the square root of 0.115. And put that on your calculator, you will get 0.34 about. Alright, so the first step would be to get the standard error. So that's 0.34. Let me erase this and we'll get the whole t-statistic. So our top here was 0.88, our r, and then divided by standard error, which we found to be 0.34. And put 0.88 divided by 0.34, and we get 2.58. And that is our t-statistic. And I'm going to round that up to 0.59 because it's 0.2588. So after you get the t-statistic, you want to put that in Excel to find the p-value. And we're going to use this t.dist. And so you just pick a random cell, and what you're going to do is just pick a random cell and start to type this in, equals t.dist, and then in parentheses. And then what I'm underlining in blue is your t-statistic. And then in orange is our degrees of freedom. And then you're just going to type in true and in the parentheses. And so this will give you the p-value, okay? Actually, it will give you the percentile. So if you type this in, it will give you this percentile. And so if we draw this out, a little t-distribution here. Actually, let me make that black. So here's our t-distribution. And here's our t of 2.59. It's about right here, it's positive. And remember, 0 is in the middle somewhere here. And the t.dist function will give you the shaded blue area, the percentile. Okay, so it gives you that. But what we want is this orange area I'm shading here, right? Because remember, our alternative hypothesis was that rho is greater than 0. We thought rho would be positive. So we want to look on the right side. Remember, when we want to look on the right side, the whole distribution is 1, so we do 1 minus the percentile to get the orange part. And the orange part is 1 minus percentile, which is 0.06. So this is actually our p-value in this example. And if we had a less than alternative hypothesis, then it would just be the blue. So if we thought rho was less than 0, it would just be this blue area. And then if we had a not equal to hypotheses for the alternative, then we would you would want to put the negative version of the t-statistic into Excel and then double that percentile. That's the easiest way to get it. So that's just a little review of how to get p-values. But you can look at, back into the other phases if you need more information about that. So step 5 to any t-test is usually the conclusion statement. And we base the conclusion statement on what our p-value is. So we had a p-value of 0.05, or I'm sorry, we had a p-value of 0.06, and our alpha level is 0.05. So this is our p, 0.06, and our alpha is 0.05. Our p-value is greater than our alpha level, so we're going to fail to reject the null. Reject our null. Okay. So that means because of that we failed to reject, we're going to say there is not. Okay? We're going to say that there is not statistically significant evidence to conclude. So that's pretty standard, that part in blue. And then this last part of the sentence is our alternative hypothesis, or research hypothesis. And remember that was rho is greater than 0. So we said there was a positive relationship, and we're talking about the relationship between the number of hours studied and the grades. So our final conclusion statement is there is not statistically significant evidence to conclude that there is a positive relationship between the number of hours studied and grades. And we can redo this with a larger n, right? Because this isn't a end-all statement. It doesn't mean that there's not a relationship between the number of hours studied and grades. It just means we didn't find a significant amount of evidence to conclude that. So particularly in this example, we have only an n of 4. So if we had a larger n, we might find it here. So just remember that this is inferential statistics, and we're just making an educated guess based on our evidence, and sometimes we just don't have a large enough n to find a difference. Or sometimes we have too big of an n and we find a difference. There is technically a difference, but the difference is just so minute that it doesn't really matter. So just keep that in mind, and that ends this video.